Warning, this is a book about malware. The links and software described in this book are malicious. Exercise extreme caution when executing unknown code and visiting untrusted URLs. For hints about creating a safe virtualized environment for malware analysis, visit Chapter 2. Don't be stupid, secure your environment. About the authors. Michael Sikorski is a computer security consultant and Mandiant. He reverse engineers malicious software in support of incident response investigations and provides specialized research and development security solutions to the company's federal client base. Mike created a series of courses in malware analysis and teaches them to a variety of audiences, including the FBI and Black Hat. He became to Mandiant from MIT Lincoln Laboratory, where he performed research in passive network mapping and penetration testing. Mark is also a graduate of the NSA's 3-year System and Network Interdisciplinary Program, SNIP. While at the NSA, he contributed to research in reverse engineering techniques and received multiple invention awards in the field of network analysis. Andrew Honig is an information assurance expert for the Department of Defense. He teaches courses on software analysis, reverse engineering, and Windows system programming at the National Cryptologic School and is a certified information system security professional. Andy is publicly credited with several zero-day exploits in VMware's virtualization products and has developed tools for detecting innovative malicious software, including malicious software in the kernel. An expert in analyzing and understanding both malicious and non-malicious software, he has over 10 years of experience as an analyst in the computer security industry. About a technical review. Stephen Lawler is the founder and president of a small computer software and security consulting firm. Stephen has been actively working in information security for over 7 years, primarily in reverse engineering, malware analysis, and vulnerability research. He was a member of the Mandiant malware analysis team and assisted with high-profile computer intrusions affecting several Fortune 100 companies. Previously, he worked in Mantech International Security and Mission Assurance SMA division, where he discovered numerous zero-day vulnerabilities and software exploitation techniques as part of ongoing software assurance efforts. In a prior life that had nothing to do with computer security, he was the lead developer for the Solna simulated component by the US Navy SMMTT program. About the contributing authors. Nick Harbour is a malware analyst at Mandiant and a seasoned veteran of the reverse engineering business. His 13-year career in information security began as a computer forensic examiner and researcher at the Department of Defense Computer Forensics Laboratory. For the last 6 years, Nick has been with Mandiant and has focused primarily on malware analysis. He is a researcher in the field of anti-reverse engineering techniques and has written several packers and code obfuscation tools such as PS Crumble. He has presented at Black Hat and DEF CON several times on the topic of anti-reverse engineering and anti-forensic techniques. He is the primary developer and teacher of a Black Hat Advanced Malware Analysis course. Lindsay Lack is a technical director at Mandiant with over 12 years of experience in information security, specializing in malware reverse engineering, network defense, and security operations. He has helped to create and operate a security operations center, led research efforts in network defense, and developed secure hosting solutions. He has previously held positions at the National Information Assurance Research Laboratory, the Executive Office of the President, EOP, Cable and Wireless, and the US Army. In addition to a bachelor's degree in computer science from Stanford University, Lindsay has also received a master's degree in computer science with an emphasis in information assurance from the Naval Postgraduate School. Gerald J. Smith is a principal consultant at Mandiant, where he specializes in malware reverse engineering and forensic analysis. In this role, he has contributed to many incident responses, assisting a range of clients from Fortune 100 companies. Prior to joining Mandiant, Jay was with the NSA, but he's not allowed to talk about that. Jay holds a bachelor's degree in electrical engineering and computer science from UC Berkeley, and a master's degree in computer science from Johns Hopkins University. Forward. Few areas of digital security seem as asymmetric as those involving malware, defensive tools, and operating systems. In the summer of 2011, I attended Peter Sikorski's keynote at Black Hat in Las Vegas, Nevada. During his talk, Mudge introduced the asymmetric nature of modern software. He explained how he analyzed 9,000 malware binaries and counted an average of 125 lines of code, LOC, for his sample set. You might argue that Mudge's samples included only simple or pedestrian malware. You might ask, what about something truly weaponized? Something like hold your breath. Stuxnet. According to Larry H. Constantine, Stuxnet included about 15,000 lines of code and was therefore 100 times the size of a 125 lines of code average malware sample. Stuxnet was highly specialized and targeted, probably accounting for its above-average size. Leaving the malware world for a moment, the text editor I'm using, Gedit, the GNOME text editor, includes gedit.c with 295 lines of code, and gedit.c is only one of 128 total source files, along with 3 more directories published in the GNOME Git source code repository for Gedit. Counting all 128 files in 3 directories yields 70,484 lines of code. The ratio of legitimate application lines of code to malware is over 500 to 1. Compared to a fairly straightforward tool like a text editor, an average malware sampler seems very efficient. Mudge's 125 lines of code number seemed a little low to me because different definitions of malware exist. Many malicious applications exist as suites, with many functions and infrastructure elements. To capture the source of malware, I counted what you could reasonably consider to be the source of elements of the COS Trojan, .c++, .object, .header, etc., and counted 253,774 lines of code. When comparing a program like Zeus to one of Mudge's average samples, we now see a ratio of over 2,000 to 1. Mudge then compared malware lines of code with counts for security products meant to intercept and defeat malicious software. He cited 10 million as his estimate for the lines of code found in modern defensive products. To make the match easier, I imagined there are products with at least 12.5 million lines of code, bringing the ratio of offensive lines of code to defensive lines of code into the 100,000 to 1 level. In other words, for every 1 line of code of offensive firepower, defenders write 100,000 lines of code of defensive bastion. Mudge also compare malware lines of code to operating systems whose malware samples are built to subvert. Analysts estimate Windows XP to be built from 45 million lines of code, and no one knows how many lines of code built Windows 7. Mudge cited 150 million as a count for modern operating systems, presumably thinking of the latest versions of Windows. Let's revise that downward to 125 million to simplify the math, and we have a 1 million to 1 ratio for size of the target operating system to size of the malicious weapon capable of abusing it. Let's stop to summarize the perspective our lines of code counting exercises produce. 120 to 1, Stuxnet to average malware. 500 to 1, simple text editor to average malware. 2000 to 1, malware suite to average malware. 100,000 to 1, defensive tool to average malware. 1 million to 1, target operating system to average malware. From a defender's point of view, the ratios of defensive tools and target operating systems to average malware samples seem fairly bleak. Even swapping the malware suite size for the average size doesn't appear to improve the defender situation very much. It looks like defenders and their vendors expend a lot of effort producing thousands of lines of code only to see it brutalized by nifty, nimble intruders sporting far fewer lines of code. What's a defender to do? The answer is to take a page out of the playbook used by any leader who is outgunned. Redefine an obstacle as an opportunity. Forget about the size of the defensive tools and target operating systems. There's not a whole lot you can do about them. Rejoice in the fact that malware samples are as small, relatively speaking, as they are. Imagine trying to understand how a defensive tool works at the source code level, where those 12.5 million lines of code are waiting. That's a daunting task, although some researchers assign themselves such pet projects. For one incredible example, read Sophale, a critical analysis of Sophos antivirus by Tavis Ormandy, also presented at Black Hat Las Vegas in 2011. The sort of mammoth analysis is the exception and not the rule. Instead of worrying about millions of lines of code, or hundreds of tens or thousands, settle into the area of 1,000 or less, the place where a significant portion of the world's malware can be found. As a defender, your primary goal with respect to malware is to determine what it does, how it manifests in your environment, and what to do about it. When dealing with reasonably sized samples and the right skills, you have a chance to answer these questions and thereby reduce the risk to enterprise. If the malware authors are ready to provide the samples, the authors of the book you are reading here are here to provide the skills. Practical Malware Analysis is a sort of book I think every malware analyst should keep handy. If you're a beginner, you're going to read the introductory, hands-on material. You need to enter the fight. If you're an intermediate practitioner, it will take you to the next level. If you're an advanced engineer, you'll find those extra gems to push you even higher, and you'll be able to say, read this fine manual when asked questions by those whom you mentor. Practical Malware Analysis is really two books in one. First, it's a text showing readers how to analyze modern malware. You could have bought the book for that reason alone and benefited greatly from its instruction. However, the authors decided to go the extra mile and essentially write the second book. This additional tome could have been called Applied Malware Analysis, and it consists of the exercises, short answers, and detailed investigations presented at the end of each chapter and in Appendix C. The authors also wrote all the malware that they use for examples, ensuring a rich yet safe environment for learning. Therefore, rather than despair at the apparent asymmetries facing digital defenders, be glad that the malware in question takes the form it currently does. Armed with books like Practical Malware Analysis, you'll have the edge you need to better detect and respond to intrusions in your enterprise or that of your clients. The authors are experts in these realms, and you will find advice extracted from the front lines, not theorized in an isolated research lab. Enjoy reading this book and know that every piece of malware you reverse engineer and scrutinize raises the opponent's cost by exposing his dark cards to the sunlight of knowledge. Richard Baitlich, Chief Security Officer, Mandiant and founder of Tau Security, Manassas Park, Virginia, January 2nd, 2012. Acknowledgements. Thanks to Lindsay Lack, Nick Harbour, and Gerald J. Smith for contributing chapters in their areas of expertise. Thanks to our technical reviewers, Stephen Law, who single-heartedly reviewed over 50 laughs on all of our chapters. Thanks to Seth Somerset, William Ballantyne, and Stephen Davis for contributing code for this book. Special thanks go to everyone at No Starch Press for their effort. Alison, Bill, Travis, and Tyler. We were glad to work with you and everyone else at No Starch Press. Individual thanks. Mike, I dedicate this book to Rebecca. I couldn't have done this without having such a supportive and loving person in my life. Andy, I'd like to thank Molly, Claire, and Eloisa for being the best family guy I could have. Introduction. The phone rings, and the networking guys tell you that you've been hacked and that your customer-sensitive information is being stolen from your network. You begin your investigation by checking your logs to identify the hosts involved. You scan the host with antivirus software to find a malicious program and catch a lucky break when it detects a Trojan horse named troj.snap.ak. You delete the file in an attempt to clean things up, and you use network capture to create an intrusion detection system, IDS, signature to make sure not all the machines are infected. Then you patch the hole that you think the attackers used to break in to ensure that it doesn't happen again. Then, several days later, the networking guys are back, telling you that sensitive data has been stolen from your network. It seems like the same attack, but you have no idea what to do. Clearly, your IDS signature failed because more machines are infected and your antivirus software isn't providing enough protection to isolate that threat. Now, upper management demands an explanation of what happened, and all you can tell them about the malware is that it was Starch.snap.ak. You don't have the answers to the most important questions, and you're looking kind of lame. How do you determine exactly what Starch.snap.ak does so you can eliminate the threat? How do you write a more efficient network signature? How can you find out if any other machines are affected with this malware? How can you make sure you've deleted the entire malware package and not just one part of it? How can you answer management's questions about what the malicious program does? All you can do is tell your boss that you need to hire expensive outside consultants because you can't protect your own network. That's not really the best way to keep your job secure. But fortunately, you were smart enough to pick up a copy of Practical Malware Analysis. The skills you learn in this book will teach you how to answer those hard questions and show you how to protect your network from malware. What is malware analysis? Malicious software, or malware, plays a part in most computer intrusion and security incidents. Any software that does something that causes harm to a user, computer, or network can be considered malware, including viruses, Trojan horses, worms, rootkits, scareware, and spyware. While the various malware incarnations do all sorts of different things, as you'll see throughout this book, as malware analysts, we have a core set of tools and techniques at our disposal for analyzing malware. Malware analysis is the art of dissecting malware to understand how it works, how to identify it, and how to defeat or eliminate it. And you don't need to be an uber hacker to perform malware analysis. With millions of malicious programs in the wild, and more encountered every day, malware analysis is critical for everyone who responds to computer security incidents, and with a shortage of malware analyst professionals, a skilled malware analyst is in serious demand. That said, this is not the book on how to find malware. Our focus is on how to analyze malware once it has been found. We focus on malware found on a Windows operating system, by far the most common operating system in use today. But the skills you learn will serve you well when analyzing malware on any operating system. We also focus on executables since they are the most common and the most difficult files that you'll encounter. At the same time, we've chosen to avoid discussing malicious scripts and Java programs. Instead, we dive deep into the methods used for dissecting advanced threats such as backdoors, covert malware, and rootkits. Prerequisites. Regardless of your background or experience with malware analysis, you'll find something useful in this book. Chapter 1 to Chapter 3 discuss basic malware analysis techniques that even those with no security or programming experience will be able to use to perform malware triage. Chapter 4 to Chapter 14 cover more intermediate material that will arm you with the major tools and skills needed to analyze the most malicious programs. These chapters do require some knowledge of programming. The more advanced material in Chapter 15 through Chapter 19 will be useful even for seasoned malware analysts because it covers strategies and techniques for analyzing even the most sophisticated malicious programs, such as programs utilizing anti-disassembly, anti-debugging, or packing techniques. This book will teach you how and when to use various malware analysis techniques. Understanding when to use a particular technique can be as important as knowing the technique, because using the wrong technique in the wrong situation can be a frustrating waste of time. We don't cover every tool because tools change all the time, and it's the core skills that are important. Also, we use realistic malware samples throughout the book, which you can download from practicalmalwareanalysis.com or starch.com/malware.htm to expose you to the types of things that you'll see when analyzing real-world malware. Practical hands-on learning. Our extensive experience teaching professional reverse engineering and malware analysis classes has taught us that students learn best when they get to practice the skills they are learning. We found that the quality of the labs is as important as the quality of the lecture, and without the lab component, it's nearly impossible to learn how to analyze malware. To that end, lab exercises at the end of most chapters allow you to practice the skills taught in that chapter. These labs challenge you with realistic malware designed to demonstrate the most common types of behavior that you'll encounter in real-world malware. The labs are designed to reinforce the concepts taught in the chapter without overwhelming you with unrelated information. Each lab includes one or more malicious files which can be downloaded from Practical Malware Analysis.com or starch.com/malware.htm. Some questions to guide you through the lab, short answers to the questions, and detailed analysis of the malware. The labs are meant to simulate realistic malware analysis scenarios. As such, they have generic file names that provide no insight into the functionality of the malware. As with real malware, you start with no information, and you'll need to use the skills you've learned to gather clues and figure out what the malware does. The amount of time required for each lab will depend on your experience. You can try to complete the lab yourself or follow along with a detailed analysis to see how the various techniques are used in practice. Most chapters contain 3 labs. The first lab is generally the easiest, and most readers should be able to complete it. The second lab is meant to be moderately difficult, and most readers will require some assistance from the solutions. The third lab is meant to be difficult, and only the most adept readers will be able to complete it without help from the solutions. What's in the book? Practical Malware Analysis begins with easy methods that can be used to get information from relatively unsophisticated malicious programs, and proceeds with increasingly complicated techniques that can be used to tackle even the most sophisticated malicious programs. Here's what you'll find in each chapter. In Chapter 0, establishes the overall process and methodology of analyzing malware. Chapter 1 teaches ways to get information from an executable without running it. Chapter 2 walks you through setting up virtual machines to use as a safe environment for running malware. Chapter 3 teaches easy to use but effective techniques for analyzing a malicious program by running it. Chapter 4, a crash course in x86 assembly, is an introduction to the x86 assembly language, which provides a foundation for using IDA Pro and performing in-depth analysis of malware. Chapter 5 shows you how to use IDA Pro, one of the most important malware analysis tools. We use IDA Pro throughout the remainder of the book. Chapter 6 provides examples of Sikorski in assembly and teaches you how to understand the high-level functionality of assembly code. Chapter 7 covers a wide range of Windows-specific concepts that are necessary for understanding malicious Windows programs. Chapter 8 explains the basics of debugging and how to use a debugger for malware analyst. Chapter 9 shows you how to use OllyDbg, the most popular debugger for malware analyst. Chapter 10 covers you how to use WinDbg debugger to analyze kernel malware and bootkits. Chapter 11 describes common malware functionality and shows you how to recognize that functionality when analyzing malware. Chapter 12 discusses how to analyze a particularly stealthy class of malicious programs that hide their execution within another process. Chapter 13 demonstrates how malware may encode data in order to make it harder to identify its activities in network traffic or on the victim host. Chapter 14 teaches you how to use malware analysis to create network signatures that outperform signatures made from captured traffic alone. Chapter 15 explains how some malware authors designed the malware so that it is hard to disassemble and how to recognize and defeat these techniques. Chapter 16 describes the tricks the malware authors use to make their code difficult to debug and how to overcome those roadblocks. Chapter 17 demonstrates techniques used by malware to make it difficult to analyze in a virtual machine and how to bypass those techniques. Chapter 18 teaches you how malware uses packing to hide its true purpose, and then provides a step-by-step approach for unpacking packed programs. Chapter 19 explains what shellcode is and presents tips and tricks specific to analyzing malicious shellcode. Chapter 20 instructs you on how C++ code looks different once it is compiled and how to perform analysis on malware created using C++. Chapter 21 discusses why malware authors may use 64-bit malware and what you need to know about the differences between x86 and x64. Appendix A briefly describes Windows functions commonly used in malware. Appendix B lists useful tools for malware analysts. Appendix C provides the solutions for the labs included in the chapters throughout the book. Our goal throughout this book is to arm you with the skills to analyze and defeat malware of all types. As you'll see, we cover a lot of material and use labs to reinforce the material. By the time you finish this book, you will have learned the skills you need to analyze any malware, including simple techniques for quickly analyzing ordinary malware and complex, sophisticated ones for analyzing even the most enigmatic malware. Let's get started. Chapter 0. Malware Analysis Primer. Before we get into the specifics of how to analyze malware, we need to define some terminology, cover common types of malware, and introduce the fundamental approaches to malware analysis. Any software that does something that causes detriment to the user, computer, or network, such as viruses, Trojan horses, worms, rootkits, scareware, and spyware, can be considered malware. While malware appears in many different forms, common techniques are used to analyze malware. Your choice of which technique to employ will depend on your goals. The goals of malware analysis. The purpose of malware analysis is usually to provide the information you need to respond to a network intrusion. Your goals will typically be to determine exactly what happened and to ensure that you've localized all infected machines and files. When analyzing suspected malware, your goal would typically be to determine exactly what a particular suspect binary can do, how to detect it on your network, and how to measure and contain its damage. Once you identify which files require full analysis, it's time to develop signatures to detect malware infections on your network. As you'll learn throughout this book, malware analysis can be used to develop host-based network signatures. Host-based signatures, or indicators, are used to detect malicious code on victim computers. These indicators often identify files created or modified by the malware or specific changes that it makes to the registry. Unlike antivirus signatures, malware indicators focus on what the malware does to a system, not on the characteristics of the malware itself, which makes them more effective in detecting malware that changes form or that has been deleted from the hard disk. Network signatures are used to detect malicious code by monitoring network traffic. Network signatures can be created without malware analysis, but signatures created with the help of malware analysis are usually far more effective, offering a higher detection rate and fewer false positives. After obtaining the signatures, the final objective is to figure out exactly how the malware works. This is often the most asked question by senior management, who want a full explanation of a major intrusion. The in-depth techniques you'll learn in this book will allow you to determine the purpose and capabilities of malicious programs. Malware analysis techniques. Most often, when performing malware analysis, you'll have only the malware executable, which won't be human readable. In order to make sense of it, you'll use a variety of tools and tricks, each revealing a small amount of information. You'll need to use a variety of tools in order to see the full picture. There are two fundamental approaches to malware analysis: static and dynamic. Static analysis involves examining the malware without running it. Dynamic analysis involves running the malware. Both techniques are further categorized as basic or advanced. Basic static analysis. Basic static analysis consists of examining the executable file without viewing the actual instructions. Basic static analysis can confirm whether a file is malicious, provide information about its functionality, and sometimes provide information that will allow you to produce simple network signatures. Basic static analysis is straightforward and can be quick, but it's largely ineffective against sophisticated malware, and it can miss important behaviors. Basic dynamic analysis. Basic dynamic analysis techniques involve running the malware and observing its behavior on the system in order to remove the infection, produce effective signatures, or both. However, before you can run malware safely, you must set up an environment that will allow you to study the running malware without risk of damage to your system or network. Like basic static analysis techniques, but basic dynamic analysis techniques can be used by most people without deep programming knowledge, but they won't be effective with all malware and can miss important functionality. Advanced static analysis. Advanced static analysis consists of reverse engineering the malware's internals by loading the executable into a disassembler and looking at the program instructions in order to discover what the program does. The instructions are executed by the CPU, so advanced static analysis tells you exactly what the program does. However, advanced static analysis is a steeper learning curve than basic static analysis and requires specialized knowledge of disassembly, code constructs, and Windows operating system concepts, all of which you'll learn in this book. Advanced dynamic analysis. Advanced dynamic analysis uses a debugger to examine the internal state of a running malicious executable. Advanced dynamic analysis techniques provide another way to extract detailed information from an executable. These techniques are most useful when you're trying to obtain the information that is difficult together with the other techniques. In this book, we'll show you how to use advanced dynamic analysis together with advanced static analysis in order to completely analyze suspected malware. Types of malware. When performing malware analysis, you will find that you can often speed up your analysis by making educated guesses about what the malware is trying to do and then confirming those hypotheses. Of course, you'll be able to make better guesses if you know the kinds of things that malware usually does. To that end, here are the categories that most malware falls into. Backdoor. Malicious code that installs itself into a computer to allow the attacker access. Backdoors usually let the attacker connect to the computer with little or no authentication and execute commands on the local system. Botnet, similar to a backdoor, in that it allows the attacker access to the system, but all computers infected with the same botnet receive the same instructions from a single command and control server. Downloader, malicious code that exists only to download other malicious code. Downloaders are commonly installed by attackers when they first gain access to a system. The downloaded program will download and install additional malicious code. Information stealing malware. Malware that collects information from a victim's computer and usually sends it to the attacker. Example includes sniffers, password hash grabbers, and keyloggers. This malware is typically used to gain access to online accounts such as email or online banking. Launcher. Malicious program used to launch other malicious programs. Usually launchers use non-traditional techniques to launch other malicious programs in order to ensure stealth or greater access to a system. Rootkit. Malicious code designed to conceal the existence of other code. Rootkits are usually paired with other malware, such as a backdoor, to allow remote access to the attacker and make the code difficult for the victim to detect. Scareware. Malware designed to frighten an infected user into buying something. It usually has a user interface that makes it look like an antivirus or other security program. It informs users that there is malicious code on their system and that the only way to get rid of it is to buy their software, when in reality the software it's selling does nothing more than remove the scareware. Spam sending malware. Malware analysis. Malware that infects a user's machine and then uses that machine to send spam. This malware generates income from attackers by allowing them to sell spam sending services. Worm or virus. Malicious code that can copy itself and infect additional computers. Malware often spans multiple categories. For example, a program might have a keylogger that collects passwords and a worm component that sends spam. Don't get too caught up in classifying malware according to its functionality. Malware can also be classified based on whether the attacker's objective is mass or targeted. Mass malware, such as scareware, takes the shotgun approach and is designed to affect as many machines as possible. Of the two objectives, it's the most common and usually the less sophisticated and easy to detect and defend against because security software targeted. Targeted malware, like a one-of-a-kind backdoor, is tailored to a specific organization. Targeted malware is a bigger threat to networks than mass malware because it's not widespread and your security products probably won't protect you from it. Without a detailed analysis of targeted malware, it is nearly impossible to protect your network against that malware and to remove infections. Targeted malware is usually very sophisticated, and your analysis will often require the advanced analysis skills covered in this book. General rules for malware analysis. We will finish this primer with several rules to keep in mind when performing analysis. First, don't get too caught up in the details. Most malware programs are large and complex, and you can't possibly understand every detail. Focus instead on the key features. When you run into difficult and complex sections, try to get the general overview before you get stuck in the weeds. Second, remember that different tools and approaches are available for different jobs. There is no one approach. Every situation is different, and the various tools and techniques that you'll learn will have similar and sometimes overlapping functionality. If you're not having luck with one tool, try another. If you get stuck, don't spend too long on any one issue. Move on to something else. Try analyzing the malware from a different angle, just try a different approach. Finally, remember that malware analysis is like a cat and mouse game. As new malware analysis techniques are developed, malware authors respond with new techniques to thwart analysis. To succeed as a malware analyst, you must be able to recognize, understand, and defeat these techniques and respond to changes in the art of malware analysis.